All right, in this video, we're going to be talking about vision and hearing. So Helen Keller said that the only thing worse than being blind is having sight and no vision. So deep thoughts. So before we talk about the process of how we see, we're going to talk a little bit about Gestalt principles. And Gestalt means a unified whole. This is our idea that we group similar elements together, that we recognize patterns, and that we simplify complex images to make it more palatable or easier for our brain to interpret. So the mind informs what the eye sees by perceiving a series of individual elements as a whole. So this is contributing to that idea of top-down processing, that our brain is actually helping our eyes figure out what we're seeing. What do I mean by this? We're going to look at 4 Gestalt principles today. The first one is the idea of closure, that our brain is going to fill in the gaps of incomplete shapes to perceive a complete image. So in this example, we see the World Wildlife Foundation's logo of a cute panda, but if we actually look at it, we notice that it's just a series of black splotches, and there's nothing connecting them together, but our brain is helping our eyes connect this image to see a series of these black splotches form this cute panda. The second idea that we're going to look at is common region, that we group elements in the same closed region together, and it makes it very easy to understand and to perceive. So if you look at your Pinterest board or Twitter feed or Instagram, most things are going to be grouped together so that we can differentiate one from the other, and that makes it just a lot easier for us to understand. If you have, a website and everything's all over the place and nothing is grouped together, it makes it really difficult for us to look at, and we don't want to look at it for very long. Another Gestalt principle is figure and ground, saying that we look at the foreground and solid items first. So if we look at this image, do you see Wolverine, the famed X-Men, or do you see 2 Batmans? Depending on your familiarity with Batman or the X-Men, might contribute to which of these you're paying attention to first. The Batman is 2 different figures in the foreground, but the Wolverine is 1 solid figure, not 2 pieces broken up. So that kind of plays a trip with our mind and our eyes, going back and forth between seeing 2 different images in the same area. And the last Gestalt principle we'll talk about is the law of proximity, the idea that we group elements that are close together and we separate them apart from those items that are further apart. So in this Girl Scout images, or Girl Scout logo image, we see 3 faces, but it's hard for us to focus on all of them at the same time. So we might group the first face and the middle face, and the middle face and the back face, but it's harder for us to see everything all together, and it gives this idea of depth. So how does vision work at all? Light waves are entering into what we call our rods and cones at the back of our retina, and rods and cones are going to help us perceive color, and those rods and cones are going to be the ones that make that chemical reaction happen, moving from a light wave into a neural impulse. Those electrical or those neural impulses are going to go through our optic nerve, to our thalamus, and then finally back to our occipital lobe. So there's actually 2 places where we're having this visual information. One is in the thalamus, and it's going to give us a quick snapshot, pretty blurry and vague information, just enough to know what is in our immediate environment. And then the second thing, not even half a second later, it's going to go back into our occipital lobe, where we're going to get more information, more details about color, about motion, lines and depth, and all that really crucial information. So here's it broken down. Light waves are entering the cornea, passing through the pupil. White wavelengths are determined by hue, determine the hue of the color, so the difference between pink and maroon, or light blue and navy blue, difference between the wavelengths. And the iris is going to focus those light rays into an image onto our retina. Interestingly, our iris also responds to thoughts and emotions to allow us to take in more information. If we like someone or see something shiny and we like it, our iris is going to focus more information or more light to allow us to see it better. So the retina is going to break down the image and convert light energy into neural impulses. And those rods and cones are going to help us with that process, transforming that light energy to neural signals via chemical reaction. If you remember from the last video, it's called transduction. And about 1 in 50 people are colorblind due to the lack of functioning cones. So when we say color blindness, typically we see this with reds and blues or reds and greens, where we may not be able to differentiate them, or they may be more muted. So you won't be able to tell the difference between like a maroon color and a pink. It's all going to be the same muddy shade of red. And finally, neural impulses are routed through the thalamus to the occipital lobe. So we have that two-part process for our brain. Thalamus, immediate reactions, and then occipital lobe is going to come in with the details and give us more information. We have a couple different theories about how we process information. The first is Gregory's visual assumption, and this is telling us that visual perception relies on top-down processing. So similar to Gestalt, that our brain is going to fill in information to help us understand what's going on. So our brain is going to take its best guess and make calculated assumptions about what an image may be. So when you're done with this video, you should come into the slides and click this Hollow Face video, and you get to experience it yourself. It's pretty trippy. The second theory we'll talk about is the binocular rivalry. It says that when our eyes are seeing two images in the same location, one image will tend to dominate the other, but we'll go back and forth, and we'll alternate periodically so we can see both of them, but we have a hard time perceiving both of them at the same time with equal clarity. So in this example, we see the words red and blue in different colors, but we may not be able to read both of them clearly when we try to see them together. We can only focus on one at a time. So now let's talk about hearing. Using our ears, and again from Helen Keller, deafness is a misfortune, for it means the loss of the most vital stimulus, the sound of the voice that brings language, sets thoughts astir, and keeps us in the intellectual company of man. Lots of deep thoughts coming out of Helen Keller. So how does hearing work in the first place? First of all, we have sound waves that are entering into our outer ear, being funneled through the ear canal and hitting our eardrum and our tiny little middle ear bones. Those vibrations in the middle ear, those little bones in the eardrum, are going to cause vibrations, which are going to cause an electrical impulse going through the cochlea. And those electrical impulses from the cochlea are going to go into our auditory nerve and into our temporal lobe. So here's it broken down. Sound waves coming in, the frequency and amplitude of sound waves produces different pitches. So the difference between a foghorn and a whistle. Those are different, vastly different frequencies and amplitudes of sound that allow us to hear them differently. So sound waves come in, causing the eardrum and those middle bones to vibrate. They are the tiniest bones in our body. We have these tiny hair cells in the cochlea that are going to vibrate or move based on those vibrations from those ear bones. So the cochlea in the inner ear is going to convert the sound waves into electrical impulses picked up by the auditory nerve. We have about 12,000 sensory cells. So think about that. In the space in here, we have 12,000 sensory cells that are moving and vibrating like this, like a little wave, to allow us to hear different frequencies and amplitudes of sound. Once those are damaged, we can have some hearing loss. So that's why we have the warnings on our phones when you have your earbuds in or your AirPods in, whatever, and it says if you listen to loud music for too long, you could result in hearing damage. This is why, because you're constantly bombarding your ears with high amplitudes of sound that are going to keep those little hairs bent over, and once they get permanently bent over, there's really no coming back from that. There's no real way to fix that. Now our ear does have the ability to adjust to loud sounds, and that's why we can go to places, like concerts or the movies and get used to the loudness of it, but it takes some time for our ears to adjust to that. And that's why we may have that ringing in our ears, that high-pitched ringing in our ears after we get done with the concert or being in a loud area, as our ears are trying to adjust again. So finally, the signals from the auditory nerve are traveling to the temporal lobe to interpret sounds. Now, since we have two temporal lobes, one on either side, and we have two ears, one on either side, we can localize sounds and figure out where sounds are coming from. If you have a profession where you have to be, talking to someone and listening to a radio or a PA system or an intercom system, you can train your brain to interpret that information differently. Medical professionals, police, firefighters, military can learn to do this over time. It's sometimes called radio ear, where you're training your brain and your temporal lobes to differentiate what's coming from my right side and what's coming from my left side. Cochlear implants are really interesting and relatively new technology, where people that have hearing loss or that are born deaf, we can bypass those middle ear bones that may not be vibrating and send sounds directly into the auditory nerve. So we have an external portion with a sound processor and a microphone, and it's going to transmit information, sound, directly to the auditory nerve via electrodes. So we're just going to bypass that whole vibration bit and go straight to the source, where we're going to convert these sound waves into electrical impulses. So for people that have hearing loss, cochlear implants are really coming up as a way to overcome deafness or severe hearing loss. It may take your brain some time to get used to it and to learn how to use it, and it's not going to be as rich of an experience because it's just a different type of sound coming in. But it's better than nothing, and really a great new way for us to train our brains if we're having that hearing loss issue. So the role of music and dopamine, I get a question a lot, why can I remember lyrics from 20 years ago, but I can't remember what I had for breakfast yesterday? Music has a really special role in our brain. Our brain likes searching for patterns, and music is full of patterns. And so our brain likes working through this ambiguity and the uncertainty of what's coming next in music. And that uncertainty and ambiguity and the hunt for a pattern produces dopamine. Remember, it's a feel-good neurotransmitter, and it helps us feel emotions while we're listening to music. And that emotional connection helps us remember music and lyrics, even 20 years later. So our auditory cortex is constantly being altered and affected by sounds around us as our brain is trying to figure out what new patterns are, and that's really exciting for our brain to do. There have been instances where with, like, say, classical music, Stravinsky's The Rite of Spring actually caused a riot the first time it was performed, because it was so assaulting and so new and so different that the theater goers weren't used to it, and caused people to lash out because they're like, oh my God, what is this? What is happening in my brain? I feel like I'm going crazy. They weren't going crazy. Their brain was just trying to figure out what was happening and producing dopamine and all sorts of emotions for them. So pretty cool stuff. The final thing we're going to talk about today is the McGurk effect in this video. It's when there is a conflict between the visual and the auditory speech. So if you are watching me talk, but you're listening to something else, your brain could be producing different sounds altogether. And your brain is trying to figure out what's going on. We call this causal inference, the process in which the brain decides whether the auditory and visual speech sounds are produced by the same source. So our brain is trying to match up what I'm saying and what you're hearing. If you watch really terrible kung fu movies and you hear them talk and then you see them talk, your brain is going to get kind of confused by that. So I want you to think about this. Stop and think. What does the McGurk effect tell us about how our brain processes visual and auditory information? And I want you to think about which you think has higher priority in the brain. If what we're seeing has higher priority, or what we're hearing has higher priority. Because obviously we have this conflict with the McGurk effect saying that if I'm talking and you're listening to something else, that your brain is gonna have some conflict and it could make up a new sound altogether to try to mesh these two sensory inputs together. So think about that. In the next video, we're going to be talking about touch and taste and smell. So I'll see you there.